This is the 5th lecture in this lecture series. It is on the approximation techniques. The steps involved in these techniques are: Step 1. Approximate the given function f of x by a simple smooth function fs of x, e.g., quadratic or cubic function. Step 2. Determine the interval containing the optimum point. Step 3. Determine the parameters of the approximating function fs of x using some selected point in the interval determined in step 2. Step 4. Use analytical methods to find the optimum point x star of fs of x. Step 5. Test the point x star in step 4 for optimality of the original problem. If yes, then stop. If no, then select the best point to use and go to step 3. Quadratic approximation. In this method, the function f of x is approximated by the quadratic function fq of x, where fq of x is this quadratic function ax squared plus bx plus c. A, b, and c are the parameters to be determined. Differentiating fq of x with respect to x and equating it to 0, we have this. The derivative of fq of x with respect to x is 2ax plus b, and then we equate this to 0. Now, solving this equation for x, we obtain the optimum point of fq of x to be x star equal to minus b all over 2a. Now, let us select 3 points, x1, x2, and x3, in the interval containing the optimum point of fq of x. At the 3 points, the values of a, b, and c can be determined as follows. We draw the x-axis and then the y-axis. Let us draw our function f of x. This is the function f of x defined over the interval from here to this point. Now we want to approximate this function f of x by a quadratic function, and to do this we are selecting 3 points in this interval. The 3 points, let us select the first point x1 here. We select the first point here x1, and the second point here x2, and then the third point here x3. Now, at this 3 point, on the curve, we have this point, and this point. So we want to draw the curve of a quadratic function to pass through these 3 points. And this is the curve given by fq of x. The optimum of this point, fq of x, is obtained at this point, which corresponds to x star. Now, to obtain the values of our parameters a, b, and c, we express the function fq of x at these 3 points. So at x1, fq of x is ax1 squared plus bx1 plus c, and this is equal to f of x1. we number this as equation 1. At the second point, x2, fq of x2 is equal to ax2 squared plus bx2 plus c, and this is equal to f of x2. Let's number this as equation 2. Then at the third point, x3, fq of x3 is equal to ax3 squared plus bx3 plus c, equal to f of x3, and we number this as equation 3. We are now ready to solve these three equations simultaneously. The simple way to do this is to use a Kramer's rule. So solving the equations 1, 2, and 3 simultaneously, we will obtain a equal to delta 1 all over delta, b equal to delta 2 all over delta, and c equals to delta 3 all over delta. Please note what we are applying here is the Kramer's rule, where delta here is the determinant of the matrix of the coefficient of a, b, and c, and delta 1 is the matrix of the coefficient in which the first column is replaced by the right hand side here. Delta 2 is the matrix of the coefficient in which the second column is replaced by the right hand side, and delta 3 is the matrix of the coefficient in which the third column is replaced by this. That is, delta is the determinant of this matrix of the coefficient. Evaluating this determinant, this will give us x1 minus x2 times x2 minus x3 times x1 minus x3. Delta 1 is this determinant, which is equal to x2 minus x3 times f of x1 plus x3 minus x1 times f of x2 plus x1 minus x2 times f of x3. Delta 2 is this determinant, and evaluating this determinant will give us x3 squared minus x2 squared times f of x1 plus x1 squared minus x3 squared times f of x2 plus x2 squared minus x1 squared times f of x3. And finally, delta 3 is this determinant. Evaluating the determinant, this will give us this: x3 times x2 squared minus x2 times x3 squared in bracket, then times f of x1 plus in bracket x1 times x3 squared minus x3 times x1 squared, then times f of x2 plus in bracket x2 times x1 squared minus x1 times x2 squared, then times f of x3. So we can now find our a, which is equal to delta 1 all over delta, and this is equal to this. Also, b is equal to delta 2 all over delta, which is equal to this. Here we don't need to determine the value of c, since what we want to find is the optimum point for our function, which only depends on a and b. That is, we recall that x star is equal to minus b all over 2a. So dividing b, that is this expression, by 2 times this expression, you will notice that the delta will cancel out. So, and this will then give us this: x star equals to minus x3 squared minus x2 squared in bracket times f of x1 plus x1 squared minus x3 squared in bracket times f of x2 plus x2 squared minus x1 squared in bracket times f of x3, all over 2 into x2 minus x3 times f of x1 plus x3 minus x1 times f of x2 plus x1 minus x2 times f of x3. Please note that if the point x1 and x2 are selected in such a way that x1 is equal to x2 minus alpha and x3 is equal to x2 plus alpha, where alpha is a constant, then our x star, which is this, will now become this, minus in bracket 2 alpha x2 plus alpha squared times f of x1 plus minus 4 alpha x2 times f of x2 plus 2 alpha x2 minus alpha squared times f of x3 all over 2 into minus alpha times f of x1 plus 2 alpha times f of x2 plus minus alpha times f of x3. Simplifying that expression, this will reduce to 2x2 plus alpha times f of x1 minus 4x2 times f of x2 plus 2x2 minus alpha times f of x3 all over 2 into f of x1 minus 2 times f of x2 plus f of x3. Now, if we open this bracket, this will give us 2x2 times f of x1 plus alpha f of x1. Here will be minus 4x2 times f of x2. And if you open this bracket, this will give us 2x2 times f of x3, then minus alpha times f of x3. So we will now obtain this. 2x2 is common, so it is factored out to give us f of x1 minus 2 f of x2 plus f of x3 in bracket, then plus alpha is common, so we factor alpha out here into f of x1 minus f of x3 all over 2 into this expression. Now, if we divide the whole of this term by this and the whole of this term by this, this will now become x2. Since these two will cancel these two and this one will cancel this, so in the first term here we will have x2 left here, then plus this one divided by the denominator. If f prime x star is equal to 0, then x star is the optimum point for our original function f of x. Otherwise, we select another set of points which are better than the previous ones to determine the values of a, b, and c. The procedure can be repeated until f prime x star equal to 0 is obtained. Example 1. Use interpolation method or approximation method to solve the following optimization problem. Minimize f of x equal to 2x squared minus exponent x over the interval 0 to 1. Solution. Let us select our 3 point x1, x2, x3 as follows. x1 equal to 0.3, x2 equals to 0.6, and x3 equals to 0.9. Please observe that the 3 point x1, x2, and x3 are all contained in the interval from 0 to 1. At this 3 point, f of x1 is equal to minus 1.17. f of x2 is equal to minus 1.10. f of x3 is equal to minus 0.8. 0.84. We recall the expression for our x star is equal to minus the whole of this. Now putting in the values for x1, x2, x3, f of x1, f of x2, and f of x3 into this expression, we will obtain x star equal to minus 0.0387 divided by minus 0.114, and this will give us 0.34. Testing this point for optimality, we have to find the first derivative of our function with respect to x, which is equal to 4x minus exponent x. Now putting in our x star here, f prime of x star is f prime of 0.34. This will be equal to 4 times 0.34 minus exponent 0.34. Evaluating this will give us minus 0.045. Clearly, this is not equal to 0. Hence, the point 0.34 is not the optimum point for our original function. So we therefore need to select a new set of points to obtain another optimum point. So if we continue, we will finally arrive at f prime of x star equal to 0. Cubic approximation. In cubic approximation, the function f of x is approximated by the cubic function denoted by fc of x, where our cubic function fc of x is this: fc of x equals to ax cubed plus bx squared plus cx plus d, where a, b, c, and d are the parameters to be determined. Now differentiating this function with respect to x, this will give us 3ax squared plus 2bx plus c, and equating this to 0, this is a quadratic equation which can be solved to obtain the optimum point for our xc of x as follows. So we use the quadratic formula to obtain x star equals to minus b plus or minus the square root of b squared minus 3ac all over 3a. The parameters a, b, c, and d can be determined by specifying f of x at 4 distinct points: x1, x2, x3, and x4. If f prime x star is equal to 0, then x star is the optimum point for our original function f of x. But if not, we have to select another set of points which are better than the previous ones to determine the values of a, b, c, and d. The procedure can then be repeated until we obtain f prime of x star to be equal to 0.